How can a lake kill more than 1,700 people without ever erupting? On a quiet night in 1986, something happened at Lake Nyos in Cameroon that left an entire landscape eerily silent. People and animals died where they stood, yet there was no lava, no ash cloud, and almost no visible sign of what had happened. The killer had come from the lake itself, but it wasn't in the water. Deep beneath the surface, an enormous amount of carbon dioxide had been building for years, hidden under pressure. And when that invisible reservoir suddenly escaped, the lake didn't need to explode. It only needed to breathe. The first thing investigators had to understand was what had actually killed the people around Lake Nyos. There was no crater blasted open, no lava had crossed the villages, no thick layer of ash covered the ground. Instead, people and livestock had simply collapsed across the surrounding valleys, while the lake itself appeared strangely undisturbed. That made the deaths difficult to explain. Lake Nyos sits inside a volcanic crater in northwestern Cameroon. Beneath its surface, however, the lake was connected to a much deeper geological system. Carbon dioxide from deep geological and magmatic sources was entering the lake and dissolving into its deepest water. Normally, that gas would eventually escape into the atmosphere. Nyos was different. Its water was strongly layered, with the deepest water remaining isolated from the surface. That allowed carbon dioxide to accumulate year after year. And this was not entirely unprecedented. In 1984, a similar gas release at nearby Lake Nyos had killed 37 people. So investigators were no longer looking for an ordinary volcanic eruption. They were looking at something quieter and potentially far more deceptive, a lake capable of storing a massive amount of gas beneath its surface. The question was no longer where the gas came from. It was how the lake suddenly released it. The strange part was that the lake did not need to erupt. A normal volcanic eruption pushes heat, rock, ash, or magma toward the surface. Lake Nyos had none of those obvious signatures. What investigators found instead was a chemical imbalance hidden in the deepest water. Carbon dioxide behaves differently under pressure. Deep underwater, pressure allows water to hold far more dissolved gas than it could at the surface. And that was the key. The deeper the gas-rich water remained, the more securely the carbon dioxide could stay trapped. So Lake Nyos could keep receiving carbon dioxide from below without immediately releasing it into the atmosphere. But that only explained how the danger had been building. It didn't explain the deaths. For the gas to escape in enormous quantities, CO2-rich deep water had to become less stable and move upward. As that water rose, the surrounding pressure dropped. Carbon dioxide began coming out of the water as bubbles. And then the physics became dangerous. Those bubbles made the water less dense, causing it to rise faster. As more water rose, even more gas escaped. More bubbles made the water rise faster still. A small disturbance could therefore become something much larger. The lake could turn a movement in its deep water into a rapidly accelerating release. Now the basic mechanism was beginning to make sense. But one critical question remained. What disturbed the deep water enough to start the chain reaction in the first place? Scientists have proposed several possibilities, including a landslide entering the lake, but the exact trigger cannot be established with complete certainty. The mechanism was becoming clear. The spark was not. The strongest evidence came from the lake itself. After the disaster, scientists sampled water from different depths and found something remarkable. The deepest layers contained extremely high concentrations of dissolved carbon dioxide. The evidence indicated that the CO2 was being supplied by deep geological and magmatic processes beneath the volcanic region, rather than by ordinary surface activity. That finding connected the first major pieces of the mystery. Carbon dioxide was entering the lake from below. The lake's layered structure was keeping that gas-rich water trapped at depth, and the amount of gas stored there was enormous. But there was another clue. The surface of Lake Nyos showed little evidence of a conventional volcanic eruption. There was no lava breaking through the water, no major ash-producing explosion, no obvious sign that magma had suddenly reached the surface. Whatever had happened, it had released a massive amount of gas without behaving like a normal volcanic eruption. Then scientists began using pipes to bring deep water toward the surface as part of a controlled degassing system. As the pressure dropped, dissolved carbon dioxide started forming bubbles. As those bubbles formed, they made the water less dense, helping drive the gas-rich water upward. This demonstrated the same physical principle that could drive a catastrophic release. Depressurization allowed dissolved CO2 to come out of solution, while the resulting bubbles helped propel the water upward. The system also provided a way to reduce the amount of gas accumulating at depth. The lake could store enormous quantities of carbon dioxide at depth, and under the right conditions, that stored gas could escape rapidly. But there was still one missing piece. How could a disturbance turn a stable, gas-filled deep layer into a runaway release? That was where the physics became truly dangerous. Now the earlier clues finally fit together. Deep beneath Lake Nyos, geological carbon dioxide was continuously entering groundwater and migrating upward into the lake. At depth, enormous pressure allowed that gas to remain dissolved in the water instead of escaping into the atmosphere. But the lake had another crucial feature. Its deepest water was effectively trapped beneath layers of warmer, less dense water above it. Without regular mixing, the carbon dioxide-rich bottom layer could continue accumulating gas year after year. The lake had become a natural gas reservoir. Then something disturbed that balance. If gas-rich deep water was suddenly pushed upward, the pressure surrounding it would begin to fall. And that changed everything. Dissolved carbon dioxide started coming out of the water as bubbles. Those bubbles made the water less dense. The lighter water rose faster. As it rose, the pressure dropped even further. More carbon dioxide escaped. More bubbles formed. More water rose. The process began feeding itself. What started as a disturbance could therefore become a rapidly accelerating release, bringing enormous quantities of carbon dioxide toward the surface in a matter of minutes. But the danger didn't end at the lake. Carbon dioxide is denser than ordinary air in extreme concentrations. It can flow downhill and collect in valleys and other low-lying areas. That meant the gas could leave the lake and move toward communities without producing a visible warning. The lake had not exploded. It had effectively released an invisible avalanche. And that may be the most unsettling part of Lake Nyos. The ingredients for the disaster had been accumulating silently for years. Only the final trigger happened in minutes. Scientists still cannot identify that trigger with absolute certainty. A landslide entering the lake is considered a plausible explanation, but the evidence does not allow every detail of that first movement to be reconstructed. What they could reconstruct was far more important. They could explain how a quiet lake had stored a deadly reservoir and how physics could suddenly release it. But now another question emerged. Could the same lake do it again? The terrifying answer was that the danger did not simply disappear after 1986. Carbon dioxide was still entering Lake Nyos from geological sources. And because the deepest water could remain isolated for long periods, the gas could begin accumulating again. The disaster had happened once. Without intervention, the same physical process could eventually become dangerous again. So scientists had to do something unusual. They installed pipes deep into the lake to bring carbon dioxide-rich water toward the surface in a controlled way. As the water rises, the pressure falls and the dissolved gas escapes gradually instead of building toward another catastrophic release. The same physics that helped explain the disaster could now be used to prevent another one. But Lake Nyos revealed something more disturbing. A volcanic hazard does not always announce itself with fire, ash, or an earthquake. Sometimes the most dangerous part of a volcanic system can remain hidden until the moment it fails. The lake was still there. The hills were still there. The villages were still there. But for a brief period, the air itself had become lethal. And that is what makes Lake Nyos so unsettling. For years, geological carbon dioxide had been quietly dissolving into the deepest water. Then, in a matter of minutes, that reservoir became a catastrophe. So when you look at Lake Nyos today, the most frightening question is not what happened in 1986. It is how something so deadly could have been hiding in plain sight for so long. The lake looked harmless. The warning was dissolved beneath the surface.